Bismillahirrahmanirrahim. Alhamdulillahi Rabbil Alamin. Hamdan shakirin, hamdan yuafi ni'amahu wa yudafi'u wa yukafi'u mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karim wa azim sultanik. Allahumma salli ala Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Yang berbahagia, Profesor Madya, Dr. Shahruddin Mahzan, Dean, Faculty of Mechanical and Manufacturing Engineering, UTHM. Our venerable guest, Professor Yoshito Ito, President of Gifu College, National Institute of Technology, Japan, and his colleagues, of course. Thank you. Deputy Deans, Assistant Registrar, fellow academic staffs of FKMP, Professor Madya, Dr. Nafarizal, Head of MINT SRC, fellow lecturers, students, ladies and gentlemen. Assalamu alaikum wa rahmatullahi wa barakatuh, and a very good afternoon. It is with great honor that I welcome you to this hall to participate in this very important event where we will be witnessing and celebrating another milestone in our relationship with our international partners. Before that, please allow me to take you through our schedule for today. Our events this afternoon will proceed with the FKMP Distinguished Lecture Series, where we will be lending our ears and minds to our esteemed speaker, Professor Dr. Yoshito Ito, who will be delivering his talk on quick absorbing structures shortly. A short Q&A session will ensue. This will then be followed with the highlight of the event at 3:45, with our Vice Chancellor giving his remarks, and followed by the Memorandum of Understanding signing between UTHM and NITGC. We will then have a short break and a quick photography session at roughly 4:15, and then end our program for today. Right. Ladies and gentlemen, the event will now proceed with the FKMP Distinguished Lecture Series. And for that, I would like everyone to join me to welcome our speaker for today, Professor Yoshito Ito, from National Institute of Technology, Gifu College, Japan, to deliver his lecture entitled Quick Absorbing Structures. So therefore, without further ado, I give you Professor Ito, please.
Yep. Yeah, thank you. Is that okay? Can you hear me? Okay. Good afternoon, everyone. I'm Ito from the Gifu College, National Institute of Technology, Japan. Yeah, 2 years ago, I was offered the president of the Gifu College. At that time, I was working at Nagoya University as a full professor, so that I have to quit the professor, but still I had a graduate student, so that I had to continue the professor, so that I'm now emeritus and yeah, is that okay? Emeritus and guest professor in Nagoya University. I'm now still working at the Nagoya University. I was the president of Gifu College. But unfortunately, salary I was given from just Gifu College. I'm a volunteer at the Nagoya University now. Is it better? Maybe this is better. Yeah, this is my arrangement. As I said, I'm now belong to two organizations, Gifu College and Nagoya University. I was born in 1952. I'm now 65, that's old. And 1977, I was assistant professor, becomes assistant professor at Nagoya University. I graduated at Nagoya University, so that including the student period, I had been working at Nagoya University for 47 years. And after that, earning Doctor of Engineering, promoted associate professor and then the full professors. And from the 2000, I became a director of university library for 9 years. Of course, as well as working as a professor. And then after that, I had been the university senator for 13 years. And during the university senator, I had been working as a director of the computer center, managing the supercomputer, internet, and education computer systems. So that I'm now the president at Gift College and then the guest and then the professor at Nagoya University. I introduced the Gifu College very briefly. We call it in Japanese Gifu Kosen. It's a special education system. This college established was in 1965, so that we have the 55 history. Number of students is 1,100, so that's not so big college, very rather small college. Number of faculty and staff members are 122, and the number of the department is 5, and we have the advanced courses, so that we give the bachelor degree. Gifu College is located in Gifu Prefecture, which is the center of Japan, just here. And we have the foreign students from the Asian countries. From the Malaysia, we have the 41 students. That's a maximum number. And Gifu College has academic exchange agreement with 11 universities, like here, Europe, USA, and Asian countries. We have already have the academic exchange agreement with UTHM in Malaysia, and today we have the new academic exchange agreement with UTHM. This is international internship and exchange student table. From the Malaysia, we have every year we have several students accepted and also dispatched. This photo is just the exchange students visiting the old city in Gifu Prefecture. This is a very brief closing ceremony. Two are from the Malaysia, I think. Nagoya University established in 1871, rather old university, and became one of the 7 imperial universities in 1942. Number of the undergrad students is almost 10,000, and the grad student is 6,000. And the number of faculty and staff members is almost 6,000. And we have the 9 schools and the 14 graduate schools. Nagoya University is one of the world leading research university. Right now we have the 6 new Nobel Prize winners. Professor Noyori and Masukawa. Professor Masukawa gave the lecture last year in Malaysia. From now, I give a brief introduction related to the research activities during the 41, I covered rather broad area of metal structures in the civil engineering. One is the strength and durability of steel members, seismic behavior of bridges, environmental impact of civil engineering structures, corrosion behavior of railings of the bridges, corrosion and durability of steel structures, and development of the new types of aluminum alloy railings. At the last part, I just touch the, I will touch the, this development of the new type of aluminum alloy railings. So far, I published 197 journal papers, and also I just present the 160 papers to the international conference. And I was given the several awards from the Japanese and British Association. This shows the research areas covered by me. This is a time. When the structure is constructed and the lifetime is, civil engineering structures, the lifetime is almost 100. And I covered almost all times, just a collision, earthquake, maintenance of bridges, fatigue, and corrosion, like here. I started the research on the buckling test and developing the database, and then earthquake, collision, environmental impact, and corrosion durability. Yeah, this is Nagoya Port Triton. Consists of 3 cable-stayed bridge constructed in 1985. When I was very young, I was as an assistant professor, I was a member of the bridge committee. So that's from the plan, experiment, construction, and the check of the completion, I just touched this project. For example, the Westgate Bridge was constructed first. When this bridge was completed, I was inside of this box girder one night to check the health of this bridge. Just during the inside this box girder, the test track just go around and check the strain and stress. This is the worldwide database of steel members done in the world. This is one example. I use this figure in the presentation. This is 958 test data of the steel columns from the worldwide, just drawing like here, and propose the design curve like here. And then I developed the database like here, using the program language in the mainframe and also the microcomputers like here. And then I just researched the behavior of the steel structures. Just applies, this is a rigid frame, very large rigid frame, almost 1/3 of the real structures. You can see the chair, size of the chair. And applying the vertical load, and also applying the cyclic loading, cyclic loading here. And then check the buckling strength of these rigid frames. And in 1995, we had a very severe earthquake called the Kobe earthquake, January 17th. Next day, just January 18th, I investigated this area, Kobe area. Maybe this is me, this is my student. Check the damage of the steel structure in the Kobe area. you can see that this elephant bulge buckling. This red color is the paint, under the paint. So that's a very big deformation occurred here. And after that, we tested in the laboratory, like here, and proposed how to repair this kind of steel structure. This is a life cycle maintenance of steel structure. You can see that this kind of very corroded pipes like here, and in the laboratory we check how to repair this kind of the corroded pipes. Just attach the steel plate using the welding undersea. And also, this is an environmental issue. Just check the emission of carbon dioxide from bridges, just to reduce the emission of the carbon dioxide, and check the various types of the bridges, and from the materials of superstructure and construction of superstructure, and the materials of substructure and construction substructure. We found the characteristic of the emission of the carbon dioxide from each part. And after that, we recommended which type of the bridges is preferable to reduce the emission of carbon dioxide. This is a collision problem of the. I did this test in Tsukuba, just a national laboratory, just an actual track collision experiment. And then using the supercomputer, model the track and the rating of bridges, everything is modeled to using the supercomputer and simulate. And like the straight guard fence, just rating, and also the curved guard fences, and also the convex curved rating, and found the characteristics of the behavior of the track and also the strength of the railings. And also, this is application of the fiber reinforced plastics in civil engineering field, rather new materials. And just apply the pedestrian bridge, and also the pedestrian bridge, and also the inspection walkways is applied, and tensile test, compression test, and also the bending test I performed. And I'll give you the one example of my research, this experimental and numerical analysis study of a newly developed bridge rating using extruded aluminum alloy. This slide was used at the Illinois University, USA, 2 years ago. Just this outline of this presentation. Usually, ratings of bridges are divided into 3 types of them. One is a flexible type made of steel or aluminum alloy. Today, just I'll deal with aluminum alloy. Another one is a rigid type, just made of concrete, and third one is a semi-rigid. This is a newly developed bridge rating using extruded aluminum alloy. This is also aluminum alloy ratings, but not the extruded, just cast of built up. And using the aluminum alloy, performance-based design is very easy, and also manufacturer expensive is, and also the freedom of design. we can expect a lot of the flexibility applying the excluded aluminum alloy. Just as this is manufacturing bridge welding post using the extruded aluminum alloy. Like here, using the male die and female die, just pressing the aluminum alloy and making this kind of the long members, and then cut that to make the post. But the limitation of the maximum press machine in Japan, almost 100 meganewton. This is a limitation, so that we had to divide it into two parts, like here. And fitting together two parts and using the stainless bolt and here. And two type of posts was tested. A type is width of flange is 155. Just imagine the velocity of the car is 45. And the B type is a rather small one, and the width is 120, and vehicle velocity just 30 kilometers. And first, we perform the static loading test of the post, like here, just putting here. This is the post. Like this is a photograph. The allowable just displacement at top is 300 millimeter, following the specification, and also check the absorbed energy. This is the result of the static loading test. This is just for A type and B type. And we can get the energy absorption and check the efficiency. And after the testing, we just make a numerical model just for the supercomputer, like here, and very precise model at just this joint we made. And this is a comparison between the test and the analysis result. Like here, very similar result, good agreement we had. After the static loading test, we performed the dynamic loading test of the post, just a heavy weight drop test. The weight is 460 kilograms, very heavy, and just dropping down. And it shows the behavior of the post. For A types, we tested 3 specimens, and B type is just only 1 specimen, like here. Time and the displacement. And after that, the numerical analysis was done, and A type and B type, and also SC type. This is just for the highway. Just the vehicle velocity is suppose 50 kilometers, like here. This is the time and the displacement. Very good performance we observed. And check the failure mode, comparison between the test and the numerical analysis. You can see the good agreements. And after that, the track collision simulation using supercomputer I performed. Just a concrete and the aluminum alloy braiding and track everything model. In Japan, the 25-ton truck is available now, so that I tried developed this kind of the model. The velocity is just 45 kilometers, and the angle of degree is 15 degrees, weight is 25. This is just following the specification. This is a result of the simulation using the supercomputer. Of course, this program was checked using the real test. And this is the result of the displacement of grading post. And maximum deformation deflection at the top is 43 millimeters. Just allowable deflection is 300 millimeters. So that this grading post is available for the real structure. And this is a check of the track model at the collision and after 0 second and 1.4 seconds. And following the specification, where vehicle guide performance, just right now the desorption speed is 36.7 kilometer. It should be the 45. It's okay. And also the desorption angle is at 2.5 degree, less than 50 degree. So that's well performance we observed. This is a real bridge railing after research. You can see this post. And also this beams also made by the extrusion. Like very beautiful railing was established. And after that, the continuous research and of the bulk extrusion model, just no joint between the two parts, just bulk model. The real bulk extrusion post was developed using German press machines with 300 meganewton installed in China. I'm sorry that in Japan this machine was not available. So that last year this new real railing was developed and constructed. Just I skipped the conclusion. This is a supercomputer at the Nagoya University. 160 teraflops is available now. Thank you for attention.
Thank you, Professor Ito. I would now like to open the floor if we have any questions. I would like to ask Professor, students, anyone interested in the research or the university or professor's background. Maybe I have one question. Professor, you mentioned about the CO2 emissions from bridges. What do you mean by CO2 emissions? Does it include the manufacturing process, fabrication, or
yeah, including everything. Manufacturing of the steel and also construction, just using the oil of the construction machine or something, everything, including everything.
And then you arrived at the conclusion that one particular design is the best in terms of CO2 emissions?
No, actually, when we construct bridges, we have several choices of types of bridges. And maybe the cost and the beauty of the type, and also emission of the carbon dioxide, and shows everything, and decide by the designer which is the best. Maybe if the importance of the environment was engineer, so maybe this weight is very, very high. And maybe ordinary engineer was fabricator, maybe think the cost is the best.
And it's always conflicting, I guess.
Yeah. That's, I never say which is the best. Just shows the materials and decide by the designer.
All right. Is it a long process, determining the CO2? Does it take long, the process of calculating, estimating the CO2
Yeah,
emissions?
it's easy. I developed the system, computer system.
All right.
And just put the type of the bridge and the weight of the material, each material, put it. And also just calculate every emission of the carbon dioxide automatically.
Brilliant. Thank you. Any other questions? Saya dah buka orang lain.
Okay, thank you, Prof. First, my name is Azlan from UTHM. So actually, it's quite a wonderful presentation for your research, and I do some attention is about your simulation on this building a bridge collision. So normally, if I'm trying to relate with the case in Malaysia. Okay, for Malaysia, is normally we are using rigid and semi-rigid railing. I can't see at all any flexible railing. So for your simulation, I just want to know what is the maximum speed of the truck they are using for the simulation?
Maximum speed is 45.
Yeah.
And
45
also
kilometer
the
per hour.
100 kilometer is also available. It's possible.
So what's the result between the 100 kilometer per hour and 45?
Yeah, just following the specification was a specific type of the railing. If we just apply the HC type, just using the highway, we have to think the more than 55 kilometers. And also the collision debris is also specified. And of course, over the such kind of specified, we can check the availability also.
Okay, thank you for that answer. Just one more question is about the carbon emission. So if we look at in Malaysia, I think if we travel to the north, we will move along a tunnel. So how about in your country or in your research? Is there any research regarding the carbon emission inside the tunnel?
Hobby. Yeah, some researchers done, but I don't think the importance of the emission of carbon dioxide is not so considered, I think. There may be one is the cost, and then the easiness of the construction and some other things. Last point is just the environment. If the other factors are the same, maybe the less carbon dioxide is behind.
Okay, thank you, Prof.
Any other questions?
Oh, yes. Okay, thank you for your interesting presentation, Prof. Ito. My name is Hazri from FCAS. I had 3 questions. Three questions, yes. I think
Each by each, yes.
I'll just
Yeah.
Okay. First is something that is not related to earthquake or railings. I find it it doesn't look, when I look at your resume just now, it doesn't look like 65 or 66. You're more like 40 something. More like my age. Okay, is there any tips for that? Essentially, you look young. Essentially, you look young.
Looks young, but the real age is very old now. But still, I'm not asking.
Okay, that is my first question. My second question, do you think Malaysia should adopt something like earthquake in their, should factor in earthquakes in their structural design and of this moment? Because a couple of years back, we had this earthquake about 6.6 Richter was felt in Penang's or our northern parts of Peninsular Malaysia. That's number two, whether we should adopt. Number three, what are the, can you explain a little bit on what are the comparison between concrete railings and your aluminum railing just now? What are the difference? I
yeah.
think, and which are the costs, in terms of costs, which are much more visible? Thank you.
Yeah, that's a question just I have to answer. The concrete railing is cheaper than the metal railing, but for the drivers, it's very dangerous. Just when the collides at the same speed, just flexible railing is very friendly for the driver. Just when the collide into the concrete, maybe the concrete is just safe. No behavior, almost no behavior. It's elastic. But when you apply the flexible railing, the inelastic behavior, just soft landing like, and also the guide the truck very safely. So that for the bridges, the flexible railing is preferred in Japan. But the cost is very high, especially the aluminum alloy is very expensive. Cost is very high rather than the steel. But the characteristic of the aluminum alloys is very high durability, and also the weight is very light. So that most engineers want to use the aluminum alloy railing, especially around the sea area. Yeah, but it's very dangerous for the drivers and the human inside the car. If the try to collide with 100 kilometer, maybe no driver survive. It's very difficult.
Yes. Second one over here.
Yes, second
My
question.
second question is a number one question.
Yeah,
Only two questions.
yeah, I don't understand the second question.
Oh, so-
Okay, I think the first question is about the implementation of this earthquake design that you implement in Japan. Whether is it possible or that we must implement in Malaysia? Because few years back ago in Sabah we have this minor impact of earthquake that will give a minor impact on the structure itself. So, for your opinion and your knowledge and your research, is it nowadays we need to look into that area? Means that in terms of design of structures, especially the high-rise building, we need to implement the earthquake resistant for the building inside.
Yeah, in Japan, just I have to explain the past. Because Kobe earthquake, we apply a very simple design way, not to apply the time dynamic response behavior. We never check it. Of course, there was a very big, large bridges I applied, but ordinary bridges we never. But after the Kobe earthquake, we were asked to apply the dynamic response behavior, apply the two types or three types of the earthquake. One is the ordinary earthquake, another one is a very severe earthquake, maybe is expected during the 1,000 years, very severe, and check the behavior of the structure, especially the energy absorption is very important. We do not want the failing of the structure, kind of failing, just the durability, just ductility is very important in structure. This is the same situation in the building structure in Japan. In Japan, the architecture people deal with building, but still applies such kind of dynamic response analysis. It's not so difficult using the supercomputer. But it's very difficult to how to design applying such kind of dynamic response analysis, because we have to choose the aspect and also the simulate the size of maybe the motion of the wave. We have to expect which motion is will have at the specific area. And if we have the measurement result, it's okay that apply such kind of aspect. But usually we don't have it. But the specification gave some type of aspect, and just choose the appropriate aspect based on the foundation.
Still have time. Professor, you can sit down if you want.
Thank you.
You can answer while sitting. Lagi? Prof. Okay, Sarudin, yeah, we have seen your simulation on your, what you call it, the extruded aluminum block. So, let's say, where is the focus? Is it the corrugated railing or the stand, the post?
You mean the extruded
Extruded
making the
post
yeah.
or the railing? Because let's say if we are to change the railing, the aluminum alloy,
No, maybe
conventional sheet metal things,
maybe. Yeah,
so
just we made the long members like here, that's two shapes, and the making the after the making the long members, we cut using the wires cutting, and this is a flange width, 150 or 130 millimeter, and make the many posts simultaneously, and then just fitting together two parts and using the stainless board at this joint.
So my question is, your work focusing on these posts. So in your simulation, you are using steel lining, steel, the railing.
Yeah, like like here.
Yeah.
Yeah.
So in any case, let's say we are using conventional sheet metal things. So is it work with your simulation or no?
You mean? Yeah, just we just develop the model of the long, just the railing totally, so that I don't understand your question. Just like there are 14 posts like here, and like the collide directly into the
Okay, Prof, I'll try to explain to you. So normally in Malaysia, we have this bridge railing. So the bottom part is concrete, and the top one is we have steel.
Yeah.
So for your simulation, is the whole part using the aluminum alloy or just the top one?
Yeah, just I did perform another research, just applying such kind of rating also. the concrete and the texture, metal structure. At that time, I used not aluminum, just steel. It's possible, but it's not so interesting because the concrete is very stiff, so that almost no behavior, just elastic. And also the height of the vehicle is high. At that time, the top railing made of metal that will be home something. But still the railing is very steep and also it's very dangerous for instance the automobile. Truck is okay, but for the automobile, the drivers should die applied to that kind of thing. So that ordinary highway we use such kind of type, but for the bridges we don't want to apply such kind of type of railing. It's very dangerous because after for example, just soft landing is very necessary to guide the vehicle against the railing.
Professor, are you okay with more questions or?
Yes.
Okay, we have one more question.
Okay, Prof, just now if you can just turn on the slide that you showed just now. The slide about
Slide,
the
oh.
trucks just now, yes.
ちょっとえどうしたのどうしたのなんか出ないの I'm sorry. Okay, which slide do you want to show?
The truck just now.
Truck?
Yeah.
Oh. This slide or this one?
Okay, the one, I think the one before, the one after.
One before.
Yeah, I think so.
No?
The other one? The same slide that you showed just now, just before you turn off.
Here?
Yes.
Yeah?
Yeah, this one. Okay, I'm actually interested. Why do you choose truck? Why truck? Is there any simulations that has been done for the cars or motorcycles? Is there a different type of vehicles?
Yeah,
Or
this
is
is following the specification. Specification asks that this type of, apply this type of truck. And also at the same time, the ordinary automobile also we are asked to try. And I tried it, and it's very safe.
Is there a simulation done for the smaller vehicles?
Yeah, but it's very difficult. I succeeded, but just the strength of the railing is no problem. Just the guidance of the automobile is very important at that time, but it's very difficult. Friction or some other issue, so that I tried several types of the automobile, but it's very difficult to develop the model, computer model of the automobile. And of course I succeeded on it, but finally we could not propose such kind of simulation in the design. It's very difficult.
Okay, if I may ask you another question. It is a very interesting studies that you have done, but is there all these studies or outcome of your research, has that been concluded and become policies in your countries?
Yeah.
It is. Okay, all right. Thank you.
I think we thank Professor Ito for the wonderful and enlightening talk there. So, ladies and gentlemen, it brings me great pleasure to invite Professor Madhya, Dr. Shahidin, to present
present our speaker today with a small token of appreciation. Prof. Ito.
後で